excitons.
You get biased excitons?
Oh, yeah, it's actually simpler than that. That's kind of a more that's a more complicated. I want to actually tell a story about basically about a single what you can understand at the level of a single exciton interacting with electrons.
Oh, okay.
And so that's
Well,
the
I know it's just
no, but yeah, it's
yeah,
like
I
yeah,
see how
yeah,
it is.
yeah. It's a problem essentially of a mobile impurity in a Fermi gas.
Okay.
That's kind of the point of view. It's a different point of view. I acknowledge it's a very different point of view, I think, from how people traditionally think about excitons and semiconductors.
I'm looking
And
for an angle because the old stuff I know that pretty well.
yeah, no,
But
I
there's
think it's
just a
different.
new
I
game.
don't. I, I must admit I don't know all the literature that well because it's. I mean,
But it's still
obviously some
pretty
of it, but
interesting.
yeah, but yeah, and it's and there's some new experiments that can see some of these signatures, and so I'll discuss relation to experiment in some way.
Well, let's get started.
Okay.
I can hear all the wires.
Yeah.
Okay, great. Let's get started. And today we have Falko, Pientka, from originally from the Neue Freie University.
Yeah, perfect. Yes.
And working with Bert Halprin here on transition metal dichalcogenides, which are two-dimensional material where the excitons are extraordinarily strongly bound. And when I was young, it was not old, worked on excitons a lot. And this is probably a totally different regime. It'd be fascinating to learn about.
All right. Well, thanks, and I'm very grateful for everyone who's here and who basically didn't go to California to the March meeting, and also chose to came here despite the nor'easter. And so I'll try to live up to that. I'm not sure I'll manage. But this talk is about excitons and semiconductors. So it's a kind of an old topic, been studied for many, many years. And I'll try to kind of shed some new light in this topic. And the work has been done. Actually, I'm working together with Bert, but this project here has been done together with Eugene and Richard Schmidt, who's here, a postdoc, and now moved to Munich. And also the group of Ataji Mamoglu and Ovidio Kudlay and his group. This is a theory collaboration, but of course, Ataji is also doing experiments that are very relevant to what we're doing, but many of these things that we're discussing are also relevant to experiments that are in Harvard going on right now, and so in SECAM as well. And so that's why I thought it's a good venue to give this talk. So the topic is electrons, excitons, and light, and some one major motivation for this work is kind of the question: can we couple photons to electrons? And that's kind of an interesting subject, because electrons you can manipulate with electric fields, with magnetic fields, and do transport. You can gate them in two-dimensional semiconductors, and those are all things that are hard to do with photons, to confine them somewhere to create gauge fields, for example. If you create a magnetic field for an electron, that's easy. But if you could couple the electron to a photon, that would realize a gauge field for the photon as well, which would be kind of pretty exciting. But of course, electrons cannot be that simply coupled to photons, because they're not polarizable. And so one strategy is to do kind of a detour and have excitons mediate an interaction between them. So because excitons are polarizable, they couple very well to photons, and that's been demonstrated in many experiments. You can put the semiconductor in a microcavity and form exciton polaritons, even, so that it can go even to a strong coupling regime. And excitons are also they're dipoles in the semiconductor, so they do interact with charges. And so the idea is that moving around electrons will move around also excitons, and they in turn will mediate a force on photons. And so that's one of the ideas. I'll not talk about. I'll talk about some elements of this in this talk, and I'll try to advance this idea theoretically, but also discuss some experimental consequences. And Yeah, the idea of coupling excitons to electrons, that's a non-trivial problem. It's a many-body problem. If you have excitons, you have electrons in the system, and they're interacting with each other. This problem, if you look at transport of electrons and whether that mediates a force on excitons, that's kind of related to another old problem in semiconductor physics, namely Coulomb drag, right? Where the idea is that you have two layers, two semiconducting layers, and you apply a force in one of them, and the only interaction between these layers is Coulomb interaction between the carriers. But because you're pulling on one electron system, the Coulomb interactions mediate that force to the second electron system, and you can measure a current in the second system as well, in the second layer. And so that's been around for some time, and you can basically apply similar ideas and think about, okay, you can now apply an electric field. Excitons are neutral, so they're not going to move in response to that field, but the electrons will move. And electrons interacting with excitons can drag them along in kind of a similar Coulomb drag type scenario. Although in this case here, this will be very different from, say, more traditional Coulomb drag experiments because the interactions turn out to be relatively strong, and actually there are non-perturbative effects of these interactions, and so there's a kind of new Coulomb drag type effect in these materials that we predict. And so that's the main topic of this talk, some kind of a rough overview. But let me go into some detail of what kind of systems do I have in mind. And I'll be thinking mostly about transition metal dichalcogenides, which I'm sure this audience doesn't really need an introduction. There's been many talks about these systems in the SICM seminar before. They're monolayers, and they come in various varieties: semi-metals, semiconductors, superconductors, even magnets. But I'll be interested in the semiconducting variants, and then say particularly tungsten diselenide, molybdenum diselenide, although it doesn't really matter that much. For my talk, I'll be interested in these materials because they have a strong exciton binding energy of the order of half an electron volt, which is of course much stronger than in like more gallium arsenide semiconductors. And so that's interesting. That gives the exciton the Bohr radius of 1 nanometer, so they're really tightly bound. And that's kind of that's actually the only reason why or most reason why I'm considering transition metal dichalcogenides. For any other purpose, I'm not going to worry about like Belli degrees of freedom, which are of course also present, and I'll only mention them briefly. But mostly I'm going to be thinking about really a caricature of a band structure in a semiconductor where there's a conduction band and a valence band, and then there's an exciton that I can excite optically, for example, and then I'm going to look at this exciton in interaction with the Fermi C if the system is doped into the conduction band. Yes.
Are the exitons mobile?
Yes. Yeah, they're mobile, so you can move around. That's very important for this discussion. Yes. And actually, I mean, this is maybe even yet too complicated. I'm not actually going to look at a conduction and a valence band. I'm actually only looking at one band and exciton as kind of some elementary excitation in the system. So I'm going to, for the most part of this talk, actually forget that the exciton consists of an electron and a hole, and treat this as a separate particle that's interacting with the Fermi C.
So in this case, you will just consider only the completely localized pieces. So you ignore all these in-gap states can be localized and filled up as traps or charges.
Oh, I'll talk about traps as well. But yeah, so I said for the most part of this talk, that's the kind of picture that I have in mind, and that's kind of justified. Say if you're looking at small densities of electrons in this conduction band, then the Fermi wavelength can be longer than a nanometer, than the Bohr radius, and then you can kind of think about these excitons really as a point-like particle, and you don't really resolve all the fine structure of that. And of course also the interaction between electrons and excitons is kind of complicated. It's kind of a dipolar interaction, and I'm not really going to worry about the details of the spatial form. I'm just going to basically model this as some attractive interaction, actually short-range attractive interaction.
So you don't worry about different effective masses of electrons and holes?
No, yeah, so the exciton has a different mass from electrons, but those are the two parameters. There's an exciton mass and there's an electron mass, whatever it is. So I don't worry about what the exciton, what the properties actually are.
But I was talking about different effective masses of electrons and holes that participate in the information.
Right.
So you don't worry about
No, I don't worry about that. I'll just, they can be different, but they will create an exciton with a certain effective mass. Yes.
The lifetime of excitons is always a transient state.
Yeah, yes. So that's true for most part. I'll consider them to be infinitely lived. I'll not specifically include this into my calculation, although, of course, I have to be aware that anything, if I want to do transport, I have to see signals below the lifetime of this in some experiment that can be done below in a time shorter than the lifetime of these excitons. And so I'll comment on that later. OK, so now I have this exciton, which is like a point-like particle moving in a system where there are electrons around. It's interacting attractively with these interactions, with these electrons. And that's kind of a well-known problem of just the mobile impurity interacting with the Fermi C. And there's several states that it can that this impurity can have, or it can do several things to lower its energy. The first one is well known, again, is called the trion, and that's just, it can bind another electron because it's attractive, it has an attractive interaction with electrons. It could just bind another electron and form a trion state. And so that trion state, of course, will have some binding energy that's much lower than the exciton binding energy, but that's something that you can potentially see in experiment. But this is not the only one, the only state, the only possibility to lower its energy for the exciton. Another possibility is, instead of binding to one particular electron, it can kind of couple to the entire Fermi C. And instead of forming a bound state, it can just create a polarization cloud. And so this is essentially, basically what it does. It moves all the, it kind of shifts all the electrons in its vicinity and creates some density profile. It's essentially Friedel oscillations around this impurity, so that there's some enhanced density near the impurity, and then there's some oscillations of the order of the Fermi wave vector. And so that's called a polaron. And if you want, you can describe this as kind of an exciton, and then there are particle hole excitations. It's dressed with particle hole excitations that are nearby, if you want. And there are actually two different states, and one is called the attractive polaron because the density is on average enhanced near the impurity, or the exciton, and the other is called the repulsive polaron, and where the kind of the density is somewhat suppressed near the exciton. And obviously, the latter one is a higher excited state because it's an attractive interaction, and yet you suppress the density. So that requires more energy than to create this state. And so this state is kind of metastable. It will always be able to decay into either a trion or an attractive polaron state. But basically, those are the three, say, important excitations of the system of an exciton interacting with this Fermi C. And maybe to give you a concrete model, the one that I discussed or that I mentioned before, I'm writing down a Hamiltonian. I'm not going to give too many equations in this talk, but I thought I'll make this specific here. So these are just a quadratic dispersion of excitons, where these X operators create excitons. It's an exciton density, and then there's electrons with some Fermi energy in the system, and then there's some interaction which is really local in space, and that means there's no structure in momentum space here in this formulation. So it's completely independent of momentum, and that means it's a contact interaction. And with this simple model, I can try to describe the system and ask what's the ground state, because that's an important question. I said this is an excited state, but the question is the trion or the attractive polaron actually the lower energy state in this system? What's more favorable for the exciton, which state to form? And so there's one very simple ansatz. I can just write down a variational wave function, which is called the Chevy ansatz, and I write down basically a wave function that's just a superposition of an exciton and an exciton plus a particle hole pair. So it's basically similar to this case, except here I said there are many quasi-particle hole pairs, because basically shifting an electron is the same as creating an electron and a hole. But here I reduce myself to one. Now that's the simplest case I can have, that there's only a single particle hole pair in the vicinity of this exciton. And by the way, maybe I should say this specifically, when I'm talking now about quasi-particle hole pairs, I really mean electrons and holes in this upper band here. I'm not talking about holes in the lower band. I'm really talking about excitation of this Fermi C here. I'm kind of, for the moment, I've forgotten that there's this other band. So I'm really talking about kind of low energy excitations of the system around the Fermi energy. All right, And so these are these electron operators here, an electron and a hole. A hole is created with C, and then the C dagger creates an electron. And then I have these variational coefficients, and I just need to basically minimize the energy and find these coefficients. That's kind of the task.
But I got confused here. Then
yes.
The excitons, which is electron hole pair, can be very large. There's no guarantee it becomes small. Right?
No, this is the exciton. The exciton is kind of a solid particle. It cannot be separated. Yeah. Yes, and these are only conduction band operators in the Fermi suit. So that's why I said they're low energy excitations around the Fermi sea in the conduction band. They're not across the gap. So there's no further excitons being formed. They're only the excitons that you basically create optically. And these quasi-particle hole pairs, they're only created through this interaction. Okay, I can write down a similar wave function, which for the trion, and I do this specifically here. So there's an exciton operator. There's these coefficients beta. There's an exciton operator, and then there's an electron operator. So that really makes the difference very clear that this is a charged particle. This is really an exciton plus a charge. So this object actually will respond to electric fields and to magnetic fields as an electron. Just has a different mass, but has the same charge. Whereas this object here is still neutral because it's just an exciton and a particle hole pair. So I haven't changed the charge of this, and there will be no direct effect of electric fields on this object. All right, and then I can solve this variational ansatz from find these coefficients, and I can plot the spectral function of this polaron state of this Chevy wave function, and that's plotted here. And so this scale here is the energy, and this is the interaction strength, and it's parameterized in kf times the scattering length. So that's a parameter that is essentially kf times the scattering length is essentially the square root of E Fermi over the binding energy of the trion. So it's some parameter that says how strongly is the system interacting, and that's determined by this ratio here. And on the right side, there's small binding, so that's called the BCS side of the crossover, and on the other side, on the left side, this is large binding. So this is the BEC side and BCS side. And you see on the weakly interacting side, first of all, you see that the attractive polaron, which is this one here, is always the ground state. It's a sharp resonance, and then all the other states are above. And it's shallow. Its binding energy is relatively small over here. So 0 is the bare exciton. And this is the binding energy here. So it's relatively shallow for weak interaction, as you would expect. So it's kind of just a mean field shift of the exciton energy in that regime. And then as you increase interaction, it kind of goes down pretty rapidly. But at the same time, it also loses quasi-particle weight. So at some point, the weight of this spectral peak here will become very small. It will actually go to 0 in the limit of very strong interactions. And at the same time, at kind of higher energies, you have this kind of broad resonance appearing. That's a repulsive polaron, as I said before. So it's kind of ill-defined on the BCS side, but it becomes increasingly well-defined on the BC side, and it also becomes increasingly stable because it can always decay into this lower attractive polaron state, but the matrix element just will become relatively small because there's very little spectral weight in this kind of state. And in between these two states, there's this what is called here molecule-hole continuum, and this is from the cold atom context. So the molecule is just our trion. So this is a trion-hole continuum that's here. And you see it's always above the attractive polaron. So that kind of answers the question, at least for this model with this ansatz. The trion is always higher in energy than the attractive polaron. But I have to say, this is an artifact of this ansatz, of this very simple wave function with just a single particle hole pair. If you were to do a more sophisticated calculation of this problem, then you'd find, and so there are quantum Monte Carlo calculations to show this, that there is actually a transition. At some point here, the trion becomes the ground state, but that happens at relatively small densities, or strong interactions, if you want, when the Fermi energy is below 1/10 of the binding energy of the trion, at least. But that's only for a model with contact interactions. So if you take into account more realistic interactions, that value may also change. So that's a question that's kind of really hard to answer because you need more than this simple model. But qualitatively, the spectral function looks pretty similar to what you see here. I should look pretty similar. There are some experiments here. So these are cold atom experiments, lithium atoms with potassium impurities in them. And it's actually in 3D where there's some differences. But qualitatively, you can see that for weak interactions, you see this attractive polaron branch here. There's a repulsive polaron branch for strong interactions. And in between, there's this broad background, which is this molecule-hole continuum that we just see in these theoretical calculations here. All right, and we can also look at the momentum resolved spectral function just for completion. So completeness, there's here this energy momentum, and there's here this red resonance is the attractive polaron, so it's really a quadratic band structure. And then at some point at higher momenta, it hybridizes with this trion hole continuum that we saw before, and up here we have the repulsive polaron. And what's important, the dashed line that I've drawn here, that's the bare exciton dispersion, just shifted in energy, so they're on top of each other. And you see that the mass is enhanced, right, of this. The red line here kind of has a larger mass than the bare exciton dispersion. And that's, of course, expected because the polaron is a state which is an exciton that has to carry around this cloud of particle-hole excitations, this density profile around it. And so basically, you would expect it to have a larger mass when it moves around. And that's actually crucial for what's to come here. All right, so this is kind of, OK, I showed this plot from this, yeah?
That's sort of might be a dumb question, but you're drawing like there's electric dipoles in the exciton, but why does that be true? Why couldn't it be spherically symmetric?
Yeah, the important thing is just that there's some. I'm not really actually modeling a dipole. This is just a caricature. I don't know what the actual. I haven't solved the actual problem of two electron a hole and another electron, and that's kind of a complicated problem also to solve. So there's some literature on that. So I'm making my life very simple. I'm just assuming I have a point particle and it's attractive, has some attractive interaction, short-range attractive interaction with other electrons around it. And I don't really care about what the actual structure of this is. And of course, you're right. In principle, in order to make any quantitative predictions, one would have to go back and assume a more realistic model. But basically, I first want to solve the problem for any model, and it's particularly so. This is kind of one instance of this many-body problem that is kind of hard to come by because it's a non-perturbative effect that we want to describe. This polaron formation actually is something that you cannot get in perturbation theory. So basically, here you see this dashed line here is a result for perturbation theory. So it's well described in the weakly interacting limit. But basically, this decay here and also this whether there's a transition or not, that's something that cannot be described in perturbation theory. So that's important. Yes?
Could you say again what the particle-hole pair, and like what is that, and how is it distinct from the exciton?
Oh, it's so basically the exciton is you take an electron from the conduction band, from the valence band, and you move it into the conduction band, and so that forms like a hydrogen atom. Right? And so that's this exciton. And the particle-hole pair that I'm talking about here is basically now I'm only including electrons. Now I think I have an exciton, and that's a fixed object. And now I'm only looking at only considering electrons in this. And now I can still kick this exciton has some interaction with these electrons, and it can kick it can basically scatter off of electrons from this Fermi C and kick them out into some higher excited state by changing its momentum. And so this would create another particle-hole pair, but only within the conduction band, within the doped conduction band. And so this is basically these C operators here, they're only conduction band operators. And these excitons comprise a conduction band and a valence band electron. And actually also the electron that I'm talking about is not the same electron as these ones, because I'm basically only considering excitons that are basically, there are two valleys, and this is where the values are important. I have basically an exciton that lives in one valley, and that's interacting with electrons in the other valley. It could also interact, of course, with electrons in the same valley, but that's something you wouldn't get any short-range interaction in that because of Pauli blocking. This electron will not go near anywhere where electrons from the same band are. And so to like the leading approximation, like you can do an approximation that this exciton basically doesn't interact with any of these electrons in this band here, and they're only interacting with electrons in this opposite band. And then you would have, of course, a copy of an exciton sitting over here and interacting with electrons over there.
In some sense, it doesn't have to be even excitons, right? Even any particles with
yes.
short-range interaction with the electrons basically will do that. Even
yes.
if I just make the phonons.
Yes.
As long as it's
yes.
kind of the short-range interaction with the electrons, yes. You'll get a very similar conclusion.
No, it's a the polaron concept is a very, very general concept. I'll be interested in excitons because I want to couple them to photons. And I can like basically control them in experiment. I can see them optically, and so that's kind of why I'm choosing excitons. But it's a very general concept, yes, indeed. Okay, so and also conversely, you don't have to couple the excitons to electrons. You can also couple it to other quasi-particles like plasmons or phonons or other. Yeah. So that's let's focus on this case. All right, but. So I described this kind of plot, but it's kind of unfortunate. So this was kind of done for these cold atom experiments. And in cold atoms, you kind of have a fixed Fermi energy, and you tune the interaction because you can tune through a Fashbach resonance. In our case, we're not going to be able, we can't tune the interactions, but we can tune the Fermi energy by gating.
Sorry about
yeah.
But in this case, your point interaction is always repulsive, or
it's attractive.
It's attractive.
It's always attractive, yes.
It's always attractive.
Yeah.
But then how you can get the repulsive part of the polaron? That's a little bit counterintuitive, right?
Yes, that's important. Yeah, but so that cannot happen in the ground state, but it can happen in an excited state. And that's another indication that the repulsive polaron needs to be the excited state because it's impossible in the ground state to get to effectively repulsive interactions. Yes. All right. So this, as I said, this is in the context of cold atoms, so here they divide by the Fermi energy, which is the constant. In our case, the Fermi energy can be tuned with the gate, and so when thinking about TMDs, we want to plot it differently and divide this through the binding energy of the exciton, which is the interaction scale, and that's fixed. And then we also want to not have a logarithmic scale, but a linear scale of the Fermi energy over binding energy, and that's kind of that's what I plot up here. So it's the same plot, just divide the energy by the binding energy and plot this scale linearly at the Fermi energy. So that's kind of doping into the conduction band, from increasing Fermi energy from 0 onwards, and the exciton initially sits at 0 energy. And then you see up here, as you dope into the conduction band, the exciton will increase in energy. That's the repulsive polaron branch. And at the same time, down here, there's a new resonance appearing, which is the attractive polaron branch, and that decreases in energy. So that's kind of the spectral function that you would expect kind of for the semiconducting perspective. And then again, there's this particle hole, there's this trion hole continuum in between here. So let's look at these experiments. So these are absorption data from this paper here, and I'm sorry for the scale. I've just rotated them from the paper, so it's hard to read. So this is the density here, and on the left part, that's the electron-doped side, and on the right side, that's the hole-doped side. And between these two zeros, then the system is in the gap. So the Fermi energy, or the Fermi energy is in the gap, and the system is neutral. And in the neutral regime, you see this broad resonance here, strong resonance, and that's the exciton peak, the bare exciton energy that you see in absorption. And you see, I hope you can see it with this projector, that this resonance indeed blue shifts as you dope into the conduction band. It also blue shifts as you dope into the valence band. And the same down here, so this molybdenum diselenide, this is tungsten diselenide, this also blue shifts. So that's at least consistent with this interpretation of a repulsive polaron branch, that the exciton at 0 kind of increases in energy. Okay, so there's another branch, and also there's another branch appearing as you dope and at somewhat lower energies, and that's also increasing with energy. Now, I want to argue that this is actually the attractive polaron, although here obviously it decreases in energy. But that actually has that discrepancy actually has a trivial origin. Namely, if you look at the spectrum of molybdenum diselenide, you see that there's the valence band has a particular spin in each valley, but say it's spin up in one valley, and then the conduction band is spin split, and the lower conduction band also has the same spin as the top valence band. And so if you want to make an exciton, you need to make it with these two bands. But of course, if you start filling this band here with electrons, then because of polyblocking, you need to basically pay a higher energy to make an exciton in the first place, and kind of to overcome a higher energy threshold to create an exciton, and that kind of shifts the overall exciton binding energy and leads to this blue shift, and that's exactly why this curve is turning upwards and not downwards. So at least that's consistent. And it's also consistent with, if you look at tungsten diselenide on the electron-doped side, you see this resonance actually decreasing in energy, and that's because the spectrum is different. Here, the spin splitting of the conduction band is opposite, and the spin-up band now is the higher one. And so if you make an exciton, you make it with this band and with this upper band here, and filling the lower band doesn't change that energy. And so therefore, you'd expect exactly this downturn of this resonance here as you would expect from calculations. On the other side, on the whole doped regime, of course, in both cases, you're kind of shifting the exciton energy because there's only one band. The other band is really much further down in energy, and so here, in both cases, you would expect a blue shift of this attractive polaron line, and that's exactly what you see here and here. Yes?
What determines the relative spin reaction with the first conduction band of each TMD? Why this first one is up and down?
I don't know. I guess there are more other experts in the audience that can answer this better than me, but yeah. There's some material-specific reason for that, which I don't know.
Traditionally, this type of the absorption has been interpreted as triangles
Yes.
rather than attractive clouds.
Yes.
How do you distinguish triangle system?
Yes. So that's the next point. An excellent point. That's, of course, you could argue that these could also be tryons. I mean, but the reason is that the tryons are very hard to see in absorption, and the reason for that is that for a tryon state, basically you need to start from the photon. A photon can excite an exciton, of course, and has a very strong, as you see here, has a very strong matrix element, so very strong oscillator strength. But if you want to make a tryon, you need to start out from an electron that initially is in the Fermi sea, an electron and a photon, and you want to end up with the tryon. And so the electron is initially an eigenstate of this momentum operator, so it's a plane wave state. And after the absorption process, it needs to be localized near the exciton. So you need to convert a plane wave into a localized state that's close to the exciton. The exciton itself can still be a plane wave state, but in relative coordinates, you need to basically make the matrix overlap between a matrix element between a plane wave state and a localized state, and that's very small. That's something that is suppressed by basically the Bohr radius of the tryon over the system size. Now, of course, you could say there are many electrons around, so I can basically have all these processes summed up, but they're all sitting at different energies, right? And so that's kind of, you see this kind of continuum of states. And as you basically increase the Fermi energy, that gets weaker and weaker because basically you have to pick up contributions from all sorts of different states. And so the contribution, there might be a contribution to tryons, but it's much smaller than the one from excitons and also exciton polarons, because for exciton polarons you don't have these small overlaps, because remember exciton polarons have a strong contribution from a bare exciton, and that gives you a significant oscillator strength. Just this first part here. Yes.
But this contact potential, you make that up? I mean,
that's unrelated. That's unrelated to the contact potential. That's a bit more general argument.
Up in order to make them that easy, right?
Yeah.
So the idea is when you bring the charge, it has electric field and it polarizes the exciton, so that you define the attraction that follows from that. But if that's weak enough, it's not going to get bound.
Mm-hmm.
And that's the picture you're in. But if it was strong enough, it would get bound.
No, it does get bound, and there's also, I don't say if you create an exciton, it can eventually, for example, form a tryon state because it's a lower energy state. What I'm saying is that the process of absorbing a photon if you need to conserve momentum basically at this, and this process you cannot just simply it's basically very unfavorable in that instance to form an exciton. You can sorry, a trion. You can form a trion later, but the basically just the phase space available for trions is suppressed when you're yes. Just in the absorption process. So it's a statement about oscillator strength of this. Yes. All right. So that's kind of the interpretation, and that's why we believe that these are actually polaron branches, not trion branches. Although I acknowledge that this is, I mean, maybe I can propose later on. I can propose other signatures of how to distinguish these, but that's at least a theoretical argument for why one should. Okay, so I want to briefly comment on some issue that was raised earlier about the having traps for excitons. So if we look at this is again another absorption. So this is rotated back. So this is now energy here, and this is gate voltage. But otherwise, it's the same plot as before. So between the dashed lines, I'm in the insulating regime, and then this is the electron doped side, and this is the hole doped side up here. And so I see the exciton line, and I see a repulsive polaron, and I see this attractive polaron. Now there are two lines, and I don't want to discuss. I don't actually have much to say of why there are two lines now, but let's just say, okay, these are attractive polarons because you can see them in absorption. But now you can look at the same kind of some part of this diagram here in photoluminescence, and these are these curves down here. And you see actually at this brown curve at the very beginning here, you see this double peak structure, which is exactly at the same energy as these, what I call attractive polarons. And so there's some small signal in photoluminescence. There's actually a larger peak at lower energies, which indicates maybe there's a trion there, which we don't see. There's nothing to be seen in absorption. Maybe that's actually the trion state, which has lower energy. So that would be one interpretation of this, which is very visible in photoluminescence because states can eventually decay into it, but you cannot form them in absorption. But I don't want to actually go on and discuss this in more detail. But let's see what happens as you dope the system, or you take carriers out, you increase gate voltage, and you go into the insulating regime, and that's the black curve back here. So this is taken from this particular paper. And then you see first there's this exciton resonance also appearing in photoluminescence. And in addition, there's this other peak down here, which is exactly at the same. There are more peaks there, but there's one peak that's exactly at the same energy as this attractive polaron states. But you don't see any signal in absorption here, although this is the same. This is kind of taking a cut here and just measuring photoluminescence rather than, this is a reflection actually rather than absorption. It carries the same information. And so what is this peak about? And so that's one scenario that you can make up is that this could be some trap state, some impurity induced. Maybe there's some atomic defects or some charge puddles in the substrate, and they bind excitons. So there's some attractive potential for them. And if enough of them have kind of roughly are of similar type and have the same energy, then you would expect a peak somewhere in this photoluminescence spectrum. You don't necessarily see that in absorption because the density might not be large enough. But as long as but basically once you excite excitons, they may eventually all fall into these traps and give a strong photoluminescence signal. And so that's kind of one interpretation for this peak. But then the obvious question arises, so why should you see this peak at exactly the same energy as the attractive polarons if this interpretation is correct in terms of these polarons? Why do they appear exactly at the same energy? And so we can write out basically a simple model for this. And basically the Hamiltonian is exactly the same as the one I showed before with excitons, electrons, and some contact interaction between them. And in addition, I've added some trap potential basically, which is the same for all, but the positions here are random in space. So there's random potentials, which all give the same binding energy, basically, for an exciton to trap. And okay, and you can write this down. You can write again, do the same wave function variational ansatz, and you get the following result, which is kind of. Let me walk you through this plot here. So this is gate voltage, so rotated back now. This is gate voltage. This is electron doped side, hole doped side. And this is energy. Again, the spectral function that we're plotting. This is the exciton resonance. And then because of this trap, there's a bound exciton resonance, which kind of the density of these traps is fairly large. So we see also a signal down here. And this is the binding energy that you get from these traps. And then there's something funny happening here. We've just assumed that these are kind of donor levels, so they get filled up as you dope the system. And so at some point, the trapping potential goes away, and that's what happens here. And so on this side, basically, you see exactly the same thing that we saw before, because all the traps are basically gone on this side, and you see repulsive polaron, attractive polaron, and a trion hole continuum. But let's look, okay, so that's less interesting. But let's look on the other side, what happens over here. And so what do we expect? Basically, what we expect is we know there's an exciton resonance that should blue shift as a repulsive polaron. At the same time, there's an attractive polaron that appears there. But now I have this additional flat state, which is this impurity bound. That, of course, does not depend on energy, so you would just continue it like that. But then, of course, both of these resonances are made up of the same excitons. So excitons can hop into the trap, and then they can hop out and form a polaron and hop back into another trap. So there will be hybridization between those, and basically what you should expect is something like this, so some avoided crossing, and that's exactly what you see here. So that's an avoided crossing between, this is where the attractive polaron should start, but it actually becomes very rapidly a massive polaron that's basically a polaron that's mostly in these traps, and very little can basically hop between traps by becoming an attractive polaron in between. And this trapped exciton here becomes an attractive polaron branch. But now the absorption properties of these two states are very different, although you don't see it from this plot here. But this state here, that depends on the density of traps. And so that's that can be very dim or hard to see in absorption, and maybe more visible in photoluminescence. But this state here is an attractive polaron, so that's very visible in absorption. And so the oscillator strength it can be very different. And so that's kind of a scenario and how you can reconcile this observation that there is an attractive polaron which starts out at the same energy. So this slope is maybe a little bit exaggerated compared to the other plot that we just saw. But there is an attractive polaron state that appears at the same energy as some state that you only see in photoluminescence, not in absorption.
I think my brain is wired to the more of the triumph pictures and then try to kind of reconcile here. One thing that I feel a little strange is this is a trap is directly for the exciton traps, right? But typical pictures I can draw is, okay, so I have the in-gap states for the just kind of electrons, right? So natural things I have to think about is it's a trap for the charges rather than trap for the exciton itself.
Oh, but if you have a Coulomb, you can still trap an exciton. The interaction is just weaker. It's just a high order interaction. But if you basically have a local charge, and local charge still interacts with the dipole, right? It's just a weaker interaction. It's a higher power law. But that's the same nature. The nature of that interaction is the same as the nature of the interaction between excitons and electrons, right? It's like a localized. You create a localized hole somewhere in your system.
If I just kind of recast this one in the triumph pictures, how much actually is the difference here?
Well, this is immobile, right? This state here is just, because in the gap you cannot have mobile triumph states, you don't have mobile charges. So that needs to be localized.
Same as kind of triumph pictures in a sense.
Yes, it's very similar, but trions need, I consider trions to be mobile particle, whereas this I would call, I mean, it doesn't need to be actually a single charge, it can be some kind of potential, right? And so that's kind of maybe the difference. All right. Okay, so that's, and then you can also look at the momentum resolved spectral function, and you also see basically this quadratic band and this flat band, and they're hybridizing. So again, the polaron becomes more massive because of this hybridization. But let me go on to transport, because that's what I want to talk about. Yes? Okay. Okay, so let's imagine I have a system with electrons in it and a single polaron. And now I act with an electric field, say, and that exerts a force on the electrons, and as a response, the electrons will accelerate. And now, okay, and now I can now the question is there a corresponding force on the exciton? So that's kind of this Coulomb drag picture. Will there be a drag force? In order to answer that question, I can go into the co-moving frame of these electrons, where all the electrons are at rest. But now I've gone into an accelerated frame, and so I need to introduce fictitious forces, right? And so the fictitious force on the polaron, or the exciton polaron, will be proportional to the bare mass of the exciton times the acceleration minus the acceleration of the electron. So that's the acceleration of this reference frame, right? And it's important that it's the bare mass because this change of reference frame doesn't know anything about the interaction and basically haven't included the level of interaction. So fictitious force really needs to be the bare mass of the exciton. But now the interactions are important because the exciton can actually not be accelerated with its bare mass. The acceleration of the polaron is determined by the polaron mass, the dressed mass. So it's because the exciton has this cloud that it has to drag along, so it's moving through honey, and its mass is actually heavier than the bare mass. And so this leads to an acceleration which is just smaller in absolute value, smaller than the electron acceleration by this mass ratio, the bare mass over the polaron mass. And now I can go back to the lab frame and add, I just have to add the acceleration of the co-moving frame, which is AE, and I get the polaron acceleration in the lab frame, which is 1 minus the mass of the exciton over the mass of the polaron times the electron acceleration. So the polarons actually accelerate, but with an acceleration that is smaller. This is smaller than 1, but a positive number. The acceleration is smaller than the electron acceleration. And so that's kind of essentially the main argument, or the main result of this polaron drag, and I'll elaborate on that. But this is the essence, that because the mass is renormalized due to the interaction with the electrons, all the interaction effects are basically captured in this mass here. If there were no interactions, the polaron mass would be equal to the exciton mass, and this would be 0. And so it's really a drag effect because it's mediated by the interactions between electrons and excitons. Yes? No, this is just an electric field, right? That will accelerate. No. Exactly. There's no direct force of the electron the exciton will not be accelerated by the electric field. There's no direct force, and that's why I'm saying it's Coulomb drag, because you're only exerting the force on one system, namely the electrons, and the other system, the excitons, feel that force only through Coulomb interactions, not because there's any direct force on them. And so that's kind of a detour going through this co-moving frame, but in that way we can understand that the drag force is really that simple. All the quantum mechanics of this polaron dressing is all contained in the difference between the bare mass and the polaron mass. All right, I can go on and just write down semi-classical equations of motion. And so basically for the electrons, I just have an electric field. I can also have some scattering due to impurities. And for polarons, I basically get a force. This is the drag force that I just wrote down due to the Coulomb interactions. And I could also have separate disorder scattering for excitons. And so there's some other relaxation term here. And if I have an alternating electric field, of course, I can solve this trivially. And for electrons, I just get the velocity that I get from Drew theory. There's no drag force on electrons because I've assumed there are very few excitons in the system, and so there's no back action. But for these polarons also have a finite velocity because of this drag, and namely the electron velocity times the mass ratio here, and then there's this other factor, I omega tau x over 1 minus I omega tau x, which is just there because of exciton disorder. So if exciton disorder is weak, or much like the scattering rate of exciton disorder is much smaller than the frequency, then this is essentially 1, and I get basically an exciton drag mobility, which is of the same order of magnitude as the electron mobility, right? Which is very different from conventional Coulomb drag, which only happens at finite temperature. So this is a zero temperature effect, and it's of the same order of magnitude rather than being a rather weak effect.
But in the DC, basically, you don't get any drag.
Yeah, well, okay, so I'll discuss that in a second. But in this case, yes. If you go to strict DC, you don't see it.
That's a little bit weird.
No, I'll come to that in a second. But yes, indeed, if it's DC, because there's no force in DC, there's the electrons will drift at a finite velocity, and I just made this argument about forces. So there's no force on the excitons, and correspondingly, there's no force on the excitons. It's the same in Coulomb drag, if you want.
And that picture now relies on the exciton being a point particle?
No, actually, it doesn't. I mean, it only relies on the effect of mass renormalization. It didn't even rely on the fact that I'm using a Fermi gas. It could also be a Bose polaron in a Bose gas. It's actually quite a quite general argument. I mean, it's of course just an argument. I need to do a calculation to corroborate that. But this argument is really just the fact that any particle that has, because of interactions, has a higher mass than its bare mass, it will experience this effect. And so in that, of course, it kind of hinges on the effect whether the polaron is a ground state or the molecules or the trion is a ground state. All these that of course depends on the details of the interaction and so on. But whether it's a stable particle. But this argument doesn't require any of that. Yes. Okay. So that's kind of the physical argument. Of course, I can do a very elaborate calculus of more sophisticated calculation, and that's what we've done. And I don't want to go into any details of this calculation. I'm just to flash what the strategy is to solve this. And basically, we're writing down a Green's function for the polaron, which is the Green's function. This is a Dyson equation here. So there's a Green's function for the exciton. So these are all red lines. Red dash is exciton, and this is a polaron line. And then there is some disorder scattering, which is these triangles here. And then there's this T matrix, which couples excitons to electrons, which are blue. And this T matrix here is nothing but a ladder diagram of interaction lines between red and blue lines. So it's an exciton. This is this contact interaction. I can sum this up as a ladder in the limit that the exciton density is small. And actually, this kind of theory, if you do it non-self-consistently, if you do really just the simplest thing, this is exactly equivalent to this Chevy wave function that I gave earlier, because you see there's just a single particle hole bubble. And that's exactly equivalent to this wave function that I wrote down with an exciton plus a single particle hole pair. So the mathematics is really identical to that. But of course, I can do this more complicated here, and I can, for example, calculate a response function, which gives me a drag conductivity. So it's an electron current, exciton current correlator that I have to calculate. And then, okay, there's the question, what's this vertex L here? And I need to go through some procedure, which is called a conserving approximation. And this is done in order to ensure that I really take into account diagrams that conserve all quantities that should be conserved, like they satisfy the continuity equation, for example. And if I go through that, I end up with two diagrams, which look kind of pretty complicated. These are called Markey-Thompson and Azamazov-Larkin diagrams. There are lots of T matrices, and there are these vertex corrections here, which have more T matrices in them. And all the T matrices need to be evaluated self-consistently. So that means these internal lines here also have little T matrices and satisfy this Dyson equation. And of course, all the lines, all the exciton and electron lines need to be broadened by disorder in order to get these effects that are taken into account. But it turns out it can be done, and we can actually calculate this analytically in the limit that the exciton density is small. And that's actually the limit we're anyway most interested in. And in that limit, we get the following result, which is exactly the same result that we got before from these very simple arguments, namely the exciton density times the mobility of electrons from the Drude theory times this mass ratio 1 minus mx over m polaron times the disorder factor I omega tau x over 1 minus I omega tau x. So this really, although this is really a full quantum mechanical theory, it boils down to the fact that all these T matrices and vertex corrections, they all go into this mass m polaron. So really, I can take into account, at least to leading order. I'm not saying that this is really the most general result, but in the simplest case, all the interactions do is really just renormalize the mass, and this argument of going between one reference frame to another reference frame and looking what the acceleration is, that this is being taken into account in this. All right, so that's, but again, this again suggests that it's an AC effect, but in fact, I can see something in a DC experiment. And so the kind of experiment that I have in mind is, of course, you apply a current to a 2D semiconductor, and then you shine in with a laser, And you look in photoluminescence, where do the excitons recombine? And if the exciton cloud kind of shifts in the direction of the carriers, then you should see photoluminescence signals basically here, and that would mean that you really have drag. And so that's the kind of experiments that you want to see. And well, so how does this look? If you apply a current to the electrons, that it turns out actually acts as kind of a vector potential on the polarons. So the polaronic dispersion that you see is shifted in momentum space. That's what a vector potential would do. And so that's kind of the translation of this polaronic drag force into a DC system that here the equilibrium the dispersion of the exciton has a minimum at a finite momentum. And that means the zero momentum polarons have a finite velocity. And it's exactly the same velocity that we had before. It's the electron drift velocity times the mass ratio that always appears there. And so if I now take a laser that excites zero momentum polarons, which in the absence of any current would just be local, they wouldn't move anywhere. There would be no overall drift of these. But in the presence of a current, they would actually move because they all have a finite drift velocity. And that's really only a consequence of this Coulomb drag and of the electron current. It's basically, you can directly derive it from the same considerations as before. So in this sense, it is also an effect that you can see in a DC experiment. All right. But of course, there's another drawback, which is the short lifetimes that was mentioned before. So lifetimes are picoseconds in monolayers, so of course, way too short to do any transport. But there's one promising alternative is to look at bilayers. Bilayers, they can well exceed, lifetimes can well exceed 100 nanoseconds because you've put electrons and holes into different layers. And then it just recombinations are suppressed because you first need to tunnel. And so you can basically apply voltage to both layers and look at that, which would not move this in the absence of any carriers, but it would move it because of drag if carriers are there. You could also look at exciton polaritons in an optical cavity where lifetimes are shorter. They're 100 picoseconds, but apparently you can still, you're still able to detect the small differences in position of these polaritons in the optical cavity. And so that's also another route. And the second route is, of course, also interesting because it allows you to actually not only move excitons, but actually also photons bound to that. So let's maybe look into that in a little bit more detail. These exciton polariton, 5 minutes, according to that. Yes, it's not that, I'm basically close to done. I have 3 more slides. So these exciton polaritons have actually been demonstrated in experiment in Atach's group. So this is the transmission line of a microcavity with a TMD inside. And this is the piezo voltage, which just tunes the length of the cavity. And that means that it shifts the resonance line. And this is the resonance line of this cavity here, function of energy. And you see these 2 avoided crossings. Here is one, and there's another here. And those are actually the attractive and repulsive polarons. So he's demonstrated actually pretty strong coupling of this cavity to these polarons. And now, well, what does the dispersion of that look like? If there's a current flowing through the system, we know that there's this shifted dispersion. And then I have this cavity mode with a really tiny mass. The mass of the cavity mode is really 10 to the 5 times smaller than the exciton mass. But if I tune it on resonance, then there's going to be a coupling here which will open this gap, and I'll get this local minimum here. And in the local minimum, I can do exactly the same calculation that I did before, the true diagrammatic calculation that I did before, and I'll get this result, which is almost the same as before. This n polaron times the electron mobility times the mass ratio times this disorder factor times a factor 1/2, because I've now exciton polaritons, and on resonance, they're half photons, half excitons. And if I'm only pulling at the exciton part, the drag conductivity is only 50% of what it is for excitons. But that's the only that's one difference. The other difference is that the scattering time now becomes very long because the density of states is just tiny here because the mass is so small. And that means the effective scattering time is much larger than the one for excitons because polaritons essentially don't feel the exciton disorder. And so this here is really unimportant on timescales of the lifetime of these particles. But that just establishes that I can do the same thing that I did with excitons with polaritons. Okay, let me maybe show the last, the last slide, or second last slide of this talk, which is I can go to magnetic field, of course, right? And that's I can just introduce a Lorentz force. So electrons are just going to move in a Lorentz force, and I can basically, okay, there's some complex notation here of the velocity vector, and in this notation, the solution of this is just the cyclotron orbits, right? It's e to the omega c. But if I plug this in, then the polaron drag equation is the same as before. And if I plug the solution in, the solution that I get is that polarons also move in cyclotron orbits with the same cyclotron frequency. Of course, because they're just feeling the Lorentz force as a drag force. The argument that I gave wasn't specific to electric fields, right? And so you can actually see cyclotron orbits of these polarons with the same frequency, although a different the radius of the orbit of the radius of the orbit is different, but the frequency is going to be the same. Sorry. No, yes, the mass is different, but it's a drag effect. It follows the electrons around the circle. It doesn't have its own. And that's very important because it's very different from tryons. Tryons would have their own cyclotron frequency, and that would be different. And that's actually one point that I wanted to make. That's a very nice signature of polarons versus tryons. They would have different cyclotron frequencies. And so you get a Hall effect of excitons and actually also of polaritons. So this is a way to generate gauge fields for photons. And the last slide, of course, you can extend this and look at, if you have cyclotron orbits, you'd expect also Landau levels of excitons, right? And so this is the same calculation that we did before. Now we only have to do it self-consistently rather than non-self-consistently. This is for, the binding energy, this is for a relatively weak field. It's larger than the cyclotron frequency. And for integer filling at small densities, at larger densities. But basically what you see is these regular levels, and these are really spaced by the cyclotron frequency. So you indeed see polaron Landau levels with the spacing omega c, whereas if you look at the tryon wave spectral function, you see them with omega 3/3, say, if the effective masses are all the same. And the tryon has 3 times the mass, roughly, of an electron. And so that's clearly as a distinction. And of course, you can go on and ask other questions. You can ask about topological phases. Can you now make a bosonic quantum Hall state with this? Because you have Landau levels and excitons are bosons. That's definitely an interesting direction. You can extend this to fractional quantum Hall system. There are actually experiments that have already been done in that regime and looking at polarons and fractional quantum Hall systems, and that's one direction that we're working on. And then there are other directions. Maybe just flash this and mention a few. You can engineer potentials for excitons and make them move around in the semiconductor. And that should, if there are enough excitons of them, that should exert a force on electrons. And so by some reverse drag effect. And so you can measure a voltage as a consequence of that. You can look at what happens if there's Bose-Einstein condensation of excitons. How does that relate to the polaronic dressing? Is there any? There should be an interplay between Bose-Einstein. There's some competition maybe between Bose-Einstein condensation of excitons and polaron dressing. You can couple this to other systems, to plasmons, of course, in these systems, also to phonons, maybe even to magnons, if you think about van der Waals heterostructures with magnetic layers. And one interesting issue is also basically the band geometry that you have in van der Waals materials. Last point, that you have a Barry curvature at the Dirac points, and you can maybe use that. You get anomalous velocities in some classics, and you can use that to steer excitons. And I'm thanking you for your attention, and I'm sorry I went over time.
So it seems that your excitons like to be polarized negative charge, and that's because you put it in the conduction band. What if you roll it down to make an exciton and put it in a hole?
It's the same story. They will always move along with the carriers. So they would move along with the electrons if the electrons are the carriers, or they would move along with the holes if the holes are the carriers in the system. Yes, they would basically move in the opposite direction if you think about electric fields. Yes, it's a screening cloud. A lot of questions.
Okay, well, thanks very much. Everybody enjoy the holiday and please sign up.
It was a great talk.
Yeah.
I have a few things kind of want to discuss, but I have to
Yeah.
for the
Sure.
conference now. So let's kind of let's talk maybe tomorrow.
Yeah.
So let me grab-
Yeah.
Maybe we have some even just the data sometimes.
Okay.
Yeah.
Yeah.